Hi ladies and gentlemen, so today we're going to be taking a look at 7.4 two-way tables. Here's the warm-up to kind of review what we talked about in 7.3, so pause the video, complete the 3 problems, and press play to see the answer. There are 4 red marbles and 2 yellow marbles in a bag. If a marble is drawn, not replaced, and another marble is drawn, find the probability that the 2 marbles drawn are both red. So the probability that the first one is red and the probability that the second one is red. So the probability that the first one is red is 4 out of 6. There's a total of 6 marbles, 4 of which are red. This specifically says, though, that things are not replaced. So this is going to be a dependent probability problem. So when I reach my hand back in the bag, I don't have 6 marbles anymore. I have 5. And I don't have 4 red ones to choose from. I have 3. And that gives me 12 out of 30 or 6 out of 15 when you reduce that down. Ooh, that reduces further to 2 out of 5. There we go. All right, number 2. The 2 marbles drawn are both yellow. So this one's going to have a similar setup. Yellow and yellow equals, well, the probability that the first one is yellow is 2 out of 6, but once we pick a yellow, there's only 1 left out of 5 marbles. So we get 2 out of 30 or 1 out of 15. And last one, the first marble is red and the second is yellow. Oops. So we have red and yellow. Well, there are 4 red marbles, so the first probability is 4 out of 6. Now, if we pick a red marble the first time, that leaves us with a total of 5 marbles. Out of those 5, how many are yellow? Well, we still have 2 yellow marbles. And we end up with 8 over 30, which reduces to 4 over 15. Right? So let's take a look at two-way tables. Imagine we ask 20 children and adults whether they like broccoli. The table shows the one way to arrange the data. And so this is kind of like the beginning of what we do when we're dealing with a two-way table, where we have kind of a response to a question, yes or no, and then we have these categories of, children and adults. So joint relative frequencies and marginal relative frequencies, these are two things that we're going to define and then apply to this broccoli example. So joint relative frequencies are found by taking values in each category and dividing by the total number of values. Marginal relative frequencies are found by adding the joint relative frequencies in each row and column. So if we're looking at this example, and this table really should not be filled out, the second one, so I am just going to white out these numbers. Here we go. All right, so the joint relative frequency is taking the numbers from each of these categories and dividing it by the total number represented in the table. This table represents a total of 20 people. We know that because in the last slide it told us it was 20. We also know that because if I took 3 plus 8 plus 2 plus 7, I would get 20. So what I'm going to do is I'm going to take each of these numbers, 3, 8, 7, and 2, and divide them each by 20 and write that proportion or that decimal in the second table. So 3 divided by 20 is 0.15, 8 divided by 20 is 0.4, 2 divided by 20 is 0.10, and 7 divided by 20 is 0.35. So this is the joint relative frequency. The marginal relative frequency is if we were to extend this table to now include totals for each column and row, that would be the marginal relative frequency. So if I take 0.15 plus 0.4, I get 0.55. 0.35 plus 0.10 is 0.45. Now if I add my columns, 0.15 plus 0.35 is 0.5. 0.4 plus 0.1 is 0.5. And also notice that the total columns both add up to 1, which should happen every time because that means it's representing 100% of the data. All right, so let's go through an example of making a two-way table. So we have this table for insurance quotes for 125 cars made by an insurance company in 1 week. Make a table of the joint and marginal relative frequencies. So what I'm going to do is I'm going to recreate the original table with teens, adults, and then a total for my columns. And then I'm going to have 0 accidents, 1 accident, 2 or more accidents, and then a total as well for a row. I know that there's 125 cars represented in this table because we're told that in the setup of the problem. So I'm going to take each of these numbers and divide by 125. So 15 divided by 125 is 0.12. 53 divided by 125 is 0.424. And that gives me a total of 0.544. 4 divided by 125 is 0.032. 32 divided by 125 is 0.256, and that gives me a total of 0.288. 9 divided by 125 is 0.072. 12 divided by 125 is 0.096, and that total is 0.168. Adding up my columns, I get 0.224 for the first column, and I get 0.776 for the second column. And now my total column and row both add to 1, so I know that I've represented all the information in this two-way frequency table. All right, let's do one more. So try this one on your own first, and then press play to see the answer. All right, so we want to make a joint and marginal relative frequency tables for the hardcover, paperback, and fiction and nonfiction book. And then we have fiction and nonfiction and total. So if I take 28 divided by, they don't tell me how many books are represented here. So this is one where we have to add them all up. And I don't have that number totaled. So let me figure out. If we do 28 plus 52 plus 94 plus 36, we get 210. So there's 210 total books represented in this table. So each number divided by 210. So 28 divided by 210 is 0.13 repeating. And I'm going to leave that repeating bar in there just to avoid some rounding errors when I do the total piece. If I do 52 divided by 210, I get 0.248. Also notice that I'm not rounding these decimals. Once you start rounding, that total, that addition of the total column and total row might not add up to 1 because of a rounding error. So I don't round when I do this division. 94 divided by 210 is 0.448. And 36 divided by 210 is 0.171. And I add up my total rows and columns, and they both give me 1, so I know I'm good to go. All right, last example problem we're going to do. We have this ballet class. We are not told how many students are in the ballet, so we are going to want to add this up, but I think it's 100, but I could be wrong. So if we add this all up, we have 38 plus 52 plus 86 plus 24. Oh no, it's 200. All right, so there are 200 dancers represented in the table. So first things first, let's create our two-way table. I already have this one set up, so you don't have to redraw it. Oops. So dividing each of the numbers by 200, I would get 0.19, 0.26, and 0.45 for the first row. Second row is 0.43, 0.12, and 0.55. And then the total row is 0.62. I'm sorry, 0.62. I don't know why I wrote a 9. Oops, there we go. And 0.38. So now let's look at the question. The question says, if you're given that a student is taking ballet, what is the probability that the student is also taking tap? This is a conditional probability. It is using this key setup of you are given something about the student. What is the probability that then this happens? So we're looking for the probability that someone is taking tap given that they are in ballet. Remember that given piece is always going to represent our denominator. So I'm given that someone is in ballet. So the total number of students that say yes to ballet is 0.62. And that's going to give me the denominator. My numerator is the overlap of those that say yes to both ballet and tap. So 0.19. Giving me an answer of 0.306. All right, so that sums up two-way tables. It's a pretty short lesson, but let myself or Mr. Brasser know if you have any questions. Have a good day.